So the purpose of this project is to use two IR sensors to measure 0 to 150 centimeter, and we're fusing the signal from these two sensors. And for that, this is the setup. The distance between the two sensors is 25 centimeter. Width-wise, it's 13 centimeter, and the height is approximately 4 centimeter of each sensor. And so this is the track we have created from 0 to 150 centimeter. And this is a white object we are using as an obstacle while we are testing whether the sensors can measure the distance properly. So this video is on fusing multiple sensors for measuring distances. So here in our project, we have two sensors, sensor 1 and sensor 2, but they are of same type, and each of these sensors can measure 20 centimeter to 150 centimeter. But we want to measure from 0 to 150 centimeter, and for that we need to use multiple sensors. So here, one sensor, like we have put one sensor behind another one that is 25 centimeter apart, so that this sensor can measure 0 to 20 centimeter that our sensor, the sensor at the front, cannot measure. Basically, sensor at the front will measure from 20 centimeter to 150 centimeter, and from 0 to 20 centimeter, which distance this sensor 1 cannot measure, will be measured by sensor 2. But for that, we have to do fusing. So how did it work? So we basically took data for each of these sensors and calibrated. So for sensor 1, we took data, all the data, and we used data from 20 centimeter to 150 centimeter to calibrate. And then for sensor 2, we did it until 30 centimeter. So we didn't do it until 20 centimeter because we wanted the range of sensor 1 and sensor 2 to overlap so that we can smoothly measure from 0 to 150 centimeter. So here we're showing the circuit diagram for staggering two different IR sensor to measure 0 to 150 centimeter. So this is sensor 1, this is sensor 2. Each of these sensor has three different wire. The first one goes to positive, the second one to ground, and the third one for the signal. And we have this Arduino and two board, one board for wire connection to each of the sensor, and we have the Arduino, which is the central component. So starting from the Arduino, we have this red wire that's connected to 5 volt, and that goes all the way to this board, and this is positive. And then on the ground pin, we have this black wire that connects to the breadboard. This pin, this row, sorry. And this also connects to the other breadboard through this wire, to this orange wire, positive to positive and negative to negative, so that both breadboard gets the power from the Arduino. Next, we explain the connection that starts from the sensor. So the positive wire, the red one, goes to the positive, the negative goes to the ground, That's pretty simple. And then the third one, which is going for the signal, for reading the analog signal, this is going to this point where there is a 4.7 kilo ohm resistor in series with that, and with the 4.7 kilo ohm resistor there is a 1 microfarad capacitor in series. So one leg, the right leg of the capacitor, is on the same point with the resistor because this is in series, and the other leg of the resistor is connected to this point where we have this yellow wire going back to the ground. And there is another wire, this green wire, that is connected to the same point where the resistor and the capacitor is connected. This is the same point. And from this point, this goes to our Arduino to pin A1. This works pretty similarly for sensor 1, where we have 3 wire. The first one goes to the first one is the yellow one, which goes to the positive on breadboard 2. The second one goes to the ground, and the third one, again the similar way, it goes to this point where there is a 4.7 kilo ohm resistor connected in series, and on the same point there is a 1 microfarad capacitor in series, and that's connected back to the ground. And the point where the resistor and the capacitor is connected in series, from that point we have this wire going back to the Arduino point A2. So that's our circuit diagram, connection for this project.
Start again.
So this is a video to test whether our sensor can measure 0 to 150 centimeter with 10% accuracy. So right now the location of our obstacle is at 0 location, and then first we move to 5 centimeter. So with 10% accuracy, our sensor should measure, the measurement should be 4.5 to 5.5. Is it 4.5 to 5.5?
Mm-hmm.
Yeah. Yeah. Next, we move to 70 centimeter. Yeah. And here, with 10% accuracy, the value should vary from 63 to 77. So it cannot go below 63. It's not going. And the maximum value should be 77. So it's less than 77. So it's good. And next we move to further and towards 105. Yeah. And here the lowest permitted value is 94.5 and 115.5. So here 90, 95, 100, 105. And the lowest value should be, lowest permissible value is 94.5. So it should be more than 94.5 and less than 115.5. So is it good?
Yep.
Okay. So let's jump to the end, which is 150 centimeter. 150 centimeter, and with 10% precision, the value should vary from 135 to 165 centimeter. Is it within the range?
Yeah. Mostly, for the most part, yeah.
Okay. So here we have a couple of IR sensors that we're using to measure distances, starting from 0 centimeter to 150 centimeter. And here we have the speaker that we're using to see how the note changes as the distance changes. So as the distance changes from 0 to 150 centimeter, it increases the as we increase the distance, the frequency of sound should increase as well. So we should be listening to different notes. So right now, the position of the obstacle is at 0 location, and we can listen to a really low frequency sound. As we move it, you can listen, the frequency of the sound is increasing with the distance. Now it's at 150 and the frequency is highest because the distance is also highest. And if we go back to 0, it should be decreasing as well with the distance. Back to 0 and the lowest frequency.